Okay, guys, we are in advanced math. We're in the third day of our unit on sequences and series. If you are in honors advanced math mods 2, 3, or 4, you are putting at the top of your paper Tuesday, April 28th, 2020. So again, mods 2, 3, and 4, this section of notes, this material, top left corner of your paper will be dated 4/28/20, Tuesday the 28th. If you're in Advanced Math Mod 7, if you are in Mod 7, this same day of notes, same title, same notes, everything you're learning, it's Monday, May 4th. We did the arithmetic sequences on Thursday the 30th. We did the geometric sequences on Friday, May 1st. It's now Monday, May 4th, 2020. So put that in your top left corner. All of you guys put for the title, Formulas / Fibonacci Sequences. Fibonacci was, I think, a French mathematician that developed the sequences we're going to look at today. Before we get to that type of sequence, remember we've already studied arithmetic and geometric. Today will be Fibonacci. They're real simple. But before we get to that, the title at the top says formulas. And what I want you to do is put a little arrow down from the word formulas first. So we're not talking about those Fibonacci sequences yet. When developing formulas that represent certain sequences, there's two forms a formula can be in. And these are the different formulas you'll see if you do take statistics next year of any kind, whether it's the College Credit Plus stats or college statistics if you're a senior and taking stats. But there's a direct formula. That's the first type of formula we're going to look at. And then the other type is called a recursion formula that we'll look at here in a second. But for now, put an arrow down from the word formulas, put a big star, write the word direct formula. Now, what is a direct formula? And by the way, we're talking about formulas used to generate sequences here. Simple little definition. A direct formula will allow you to find any term at any time without knowing any other term in that sequence. Because you've got, like it says, a formula that tells you, generates directly the sequence that we're creating. So again, quick definition for direct formula. It's a formula that you can find any term of the sequence at any time without knowing any other term. It's literally a formula representing the sequence of numbers you're going to generate. So my first example, so go ahead and put EX for example, says 26 minus 3n. Now, right now, if I said to you, hey, what is that? Is that a arithmetic sequence, a geometric sequence? Neither. You can't really tell yet since we haven't worked with these much just from looking at it. But once we generate the first few numbers, obviously, we'll be looking for a pattern and be able to answer that question. Now, how do you generate a sequence of numbers from that direct formula? Well, it's real simple. Obviously, n is a variable, your unknown. Hey, guys, term 1, this is just a little note in parentheses here. Term 1 of the sequence is found by letting n equal 1. Term number 2 is found by letting n equal 2. Term number 3, the third number in our sequence, is found by letting n equal 3, and so on. So if the direct formula is represented by 26 minus 3n, and I said write down the first three numbers, well, obviously when we plug a 1 in for the first number here, 3 times 1 is 3, and 26 minus 3 is 23. Plug in a 2. 3 times 2 is 6. 26 minus 6 is 20. Plug in a 3. 3 times 3 is 9. 26 minus 9, 17. ... So you can tell, now that we've got three numbers to establish a pattern, that what? We're adding -3 every time. So that really is an arithmetic sequence whose common difference is -3 generated by that direct formula. So if I said to you, what's the 17th term? Well, I guess now that we know it's arithmetic, we could go back to which formula did you use to find the nth term of an arithmetic sequence? Review question. Wasn't that a sub n equals a sub 1 plus n minus 1 times d? Well, instead of that, since we know the name of the direct formula generating the sequence of numbers, we could simply plug 17 in for n, couldn't we? So we'd have 26 minus 3 times 17. So that'd be what? 26 minus 51. So the 17th term of that sequence would be negative 25. Okay? All right. Now, the next direct formula says n squared plus 2n. So basically, any formula that you create is fine, and you can use it to directly generate a sequence of numbers by plugging in 1 for n, then 2 for n, then 3 for n, etc. So right now, if I plug 1 in, obviously 1 squared is 1. 2 times 1 is 2. 1 plus 2, my first 4 terms, the first term would be 3. Agreed? Plug in 2 for n, because it's my second term that I'm seeking. 2 squared is 4. 2 times 2 is 4. So 4 plus 4 gives me 8. Now, guys, freeze. Do not say, oh, must be arithmetic, and the common difference is 5. I kind of doubt the next number is going to be 5 more than 8. Let's see. Maybe it is, but I doubt it. What's 3 squared? 9. 2 times 3 is 6. 9 plus 6 is 15. Plug 4 in, because it said let's find the first 4 terms. 4 squared is 16. 2 times 4 is what? 8. 16 plus 8, 24. So there is a pattern here, agreed? We added 5, then we added 7, then we added 9. So there are direct formulas that create a sequence of numbers that have a pattern. That just doesn't happen to be arithmetic or geometric, either one, okay? So if I said, hey, what's the 11th term? Well, again, similar to what we pointed out the first day of notes we took, I really don't need to write out all 11 of them, do I? I can plug 11 into my direct formula. So 11 squared is what? 121. 2 times 11 is 22. So 121 plus 22 would be what? 143. And I should be able to find my 11th term. Okay? The other way that a sequence can be represented instead of a direct formula is something called a recursion formula. Now, a recursion formula is obviously different, or it wouldn't be a second kind here. The little note I've got next to recursion formula says, focus on the first term and then focus on what would be, quote, the next term. You've always got a first term given to you, and then you got to calculate or figure out what would the next term look like. So in terms of symbolism, look at the example I've created, the first one here. If I look at this first example, okay, ignore the second one here for a minute. It says A1 is 23. So they're focusing on what the first term is. They give you that the first term is 23, and A sub n is found by taking a sub n minus 1 and subtracting 3. What? Okay, well, let's use this once. Obviously, if I was going to write down the first few numbers of this sequence, A1, my first number, it said, is 23. So I write down 23. Okay, now, since we've got the first number, do you agree we're now looking for the second number, the second term? So if that's true, this is now a sub 2 that I'm looking for. Agreed? I'm looking for the second term. Well, a sub 2 minus 1 is 1. So you take the first term, which was 23, and subtract 3, giving you 20. And that's how I got my second term. Now, what's the third term going to be? Now, I've already written it, but watch. Pretend it's not there for a second. If I'm now looking for the third term, that makes this value here that I'm pointing at a sub 3, doesn't it? So watch this, guys. I'd have a sub 3 equals a sub 3 minus 1. So that would be a sub 2, which means what? Means the second term. Well, we already said the second term's 20. So 20 minus 3 gives me, oh, that's where the 17 came from. So that is an arithmetic sequence whose difference is 3. That's the exact same sequence that we generated up here in example number 1, but one was a direct formula, and this is called a recursion formula. Let's try another one like that. Look at this. All right. It says A1 is 11. So my first term of some random sequence is 11. My nth term is 2 times a sub n minus 1. Doesn't that in essence mean 2 times whatever the last term was? Because I'm looking for a sub n, and I'm taking 2 times a sub n minus 1, which always represents the last term that we had in our sequence. And then, oh, by the way, let's add 6. So let's see if we can find the first 4 terms of that sequence. Well, duh, a sub 1, my first term, we know is 11. Okay, this is the type of thing you got to do for homework here. Let's see if we can do it. Could you find the next term of that sequence? In other words, what's the second term going to be? Using my recursion formula here, a sub 2, because I want to know what's the second term, would be 2 times, now that says a sub n minus 1. Since I'm looking for the second term, my n would be 2, wouldn't it? So 2 minus 1, oh, is 1. So really I'm thinking what's 2 times the first term, which is 11. So 2 times 11 is what? 22 plus 6 gives me, 2 times 11 was 22 plus 6 gives me 28 for my second number. Okay, hang in there with me. What are we looking for now? We're looking for the third term, aren't we? So I'm looking for a sub 3. So it's going to be a sub 3, so obviously n is 3 here, equals 2 times, okay, a sub 3 minus 1. Well, 3 minus 1 is 2, and a sub 2, our second term, was 28, wasn't it? So you take 2 times the last number, which was 28, and then you add 6. I get what? 56 plus 6 is 62. And finally, what would the fourth term be? Well, a sub 4 is going to be, according to the recursion formula, 2 times a sub 4 minus 1, which is the third term, right? Well, the third term was 62. So 2 times 62 plus 6, what is that? 124 plus 6 gives me 130. And I did indeed generate the first 4 numbers. Notice that is not, again, an arithmetic sequence, right? It's not even a geometric sequence. It is a sequence. It does have a pattern, believe it or not. And that pattern is created by that recursion formula. Okay? So, arithmetic geometric sequences, they can be created by what's called direct formulas and recursion formulas. You've been introduced to those. And the final kind of sequence we're going to give you here at the beginning of this chapter is called a Fibonacci sequence. Now, I'm going to cover up the little definition here. Look at this sequence. 1, 3, 4, 7, 11, 18. What is the pattern there? If I just said to you, what would the next number be? I'll give you a few seconds here. Think about it. Do you see a pattern? And can you come up with the next number? Okay, guys. The definition of a Fibonacci sequence is, so just put a little definition on your paper. It says, each term of this sequence after the second term is the sum of the previous 2 terms. Oh, look at that question again. What's 1 plus 3? 4. What's 3 plus 4? 7. 4 plus 7, 11. 7 plus 11, 18. So obviously don't count the first two as part of that pattern. They could be any two numbers. They could be the same number twice in a row. Who knows? But the second you realize you're taking a number plus a number to get the next number, then a number plus a number to get the next, when you take the previous two terms and add them together to get the next number, that's called a Fibonacci sequence. Okay, it's obviously not arithmetic, not geometric, but it is a sequence of numbers that has a pattern. You just got to find it. So by getting introduced to these different types, at least now you know what to look for as you get to statistical situations. Okay, so let's try a couple of those. First example, I've got 2, 2, 4. Okay, obviously that's not arithmetic, is it? Because I added 0. Then I added 2, then I added 4, then 6, and I'm not multiplying by the same number. They are in ascending order, they're getting bigger. What would the next three terms be? Well, let's find the pattern. Does it fit the description we just made? I think so, right? We look at the first two, they're irrelevant. If I add 2 and 2, I get 4. 2 and 4 gives me 6, 4 and 6 gives me 10, 6 and 10 gives me 16. Your thought is, that's a Fibonacci sequence. My next three terms, okay, I don't think we're going to need a calculator, are we? 10 plus 6, 26. Now, that means 16, 26 are my last two numbers, right? So add them up and we get what? 42? Add those two up and we would get what? 68. And we follow our pattern. Okay? And you could even have fractions for a Fibonacci sequence. Again, most people, show this to your parents. See if somebody picks it out. A half, 1, 1.5, 2.5, 4. So you think anybody in your family can find the pattern without giving them that definition? Well, look, you guys know to look for this now. A half plus a half is a whole. A half plus 1 is 1.5. 1 plus 1.5 is 2.5. 1.5 plus 2.5 is 4. Let's keep going. 2.5 plus 4 is 6.5. 4 plus 6.5 is 10.5. 6.5 plus 10.5 is what? 17. 10.5 plus 17, 27.5. We could keep going. We recognized it was a Fibonacci sequence and we were able to find the next three numbers. Okay? All right, good. Homework. Not difficult at all. This is not meant to be a difficult chapter. It's just introducing you to the concept of sequences and series. We've done sequences for 3 days. Tomorrow we will start arithmetic geometric series. It sounds like it's just a one-word difference. What's the difference between a sequence and a series? Well, you'll see tomorrow, and we'll kind of go from there, okay? Homework, I would hit pause. All you're doing, guys, on all 6 of these problems in your assignment is just go ahead and find either the first 3 terms or the next 3 terms, depending on the problem that's given. So find the next 3 numbers of this sequence. It looks like you've got 2 what? Direct formulas? 2 what? Recursion formulas, and 2 probably what? Fibonacci sequences. Can you get me the first 3 or the next 3 numbers of each of these 6 sequences? So hit pause, copy all 6 of these down, and simply take 5, 6, 7 minutes, big deal, and find the next 3 numbers of each of those sequences. Okay? Great job. Again, we'll go to series tomorrow as opposed to sequences and look at some of the things we can do with that. We'll see you then.